The focus of this lesson is on graphing a rational function. So in order to do that, we're going to start off by factoring the rational function. So up top we have x squared minus 6x plus 8. So that trinomial factors into, just kind of think the reverse of FOILing, what two numbers multiply together to give you positive 8 but add to give you negative 6, and you would get negative 4 and negative 2. Then do the same thing for the denominator. What two numbers multiply together to give you negative 12, but add together to give you negative 1, and you would come up with negative 4 and positive 3. So as you can see, we do have a factor that cancels, the x minus 4, and when the factor cancels, the zero of that factor would be considered a whole of our rational function. So there's a whole at where that factor equals 0, so where x minus 4 equals 0. But that, if you think about it, if you add 4 to both sides, that means you have a whole at x is 4. Then we can kind of move on to our next step, which is where we find our x-intercepts and our vertical asymptotes. Recall your x-intercepts are basically the zeros of your rational function. So our x-intercepts or zeros occur from setting the numerator's factors equal to 0. So if we set x minus 2 equal to 0, and again, if you add 2 to both sides, you would see that you're left with x equals 2 is a 0 of our rational function. And then from the denominator, that's where you're undefined, and so that's what's going to produce your vertical asymptotes, so the 0 of your denominator. So x plus 3 equals 0. And again, sometimes it's just obvious, so you don't have to show all of this work, but I just want you to see the work in case you need it. But again, x equals negative 3 is what value would make that denominator 0, and x equals 2 is what value would make the numerator 0. So we found the zeros and we found the vertical asymptotes. So from a graphical perspective, so I'm going to go ahead and draw a Cartesian coordinate plane. We have a 0 at x equals 2, so go 2 tick marks out, and then we have a vertical asymptote at x equals negative 3. And a vertical asymptote is a line, so it needs to be expressed as that line. So then if I go ahead and plot these values, when x is 2, that's where we're hitting the x-axis because that's the x-intercept at our 0. And then we have a vertical asymptote at x equals negative 3. So then what we have to do is we have to determine, well, what is the behavior to the left and to the right of the vertical asymptote and to the left and the right of the 0. So in other words, we have to take our function h, and you can look at the factored form, like where we've already done the canceling, and we need to evaluate it at some test points. And the test points we're going to use is something like maybe a tenth to the left of the vertical asymptote and a tenth to the right, and then do the same thing for the zeros, a tenth to the left and a tenth to the right of the 0. So if we look at our vertical asymptote, we have it at x equals negative 3. Well, to the left of that is negative 3.1. To the right of that would be negative 2.9. And then to the left of our 0 would be 1.9, since our 0 occurs at x equals 2. And to the right of that would be 2.1. So I just moved a tenth to the left and a tenth to the right. And then what I would do is, I don't care so much about what value I get back, but I do care about the sign. So I would take my function and evaluate it at each of these values. So at negative 3.1, I'd plug that in for my x, and I'd see up in the numerator that a negative 3.1 minus 2 gives me a negative. And in the denominator, negative 3.1 plus 3 gives me a negative as well. And then a negative divided by a negative is overall positive. So what that means is, for my graph, to the left of negative 3, so at like negative 3.1, I'm positive. So that means I shoot to positive infinity. So I'm just going to draw an arrowhead signifying that. And then I do the same test with maybe negative 2.9, so to the right of that vertical asymptote. Negative 2.9 minus 2 is going to give us back something negative. Negative 2.9 plus 3, something positive. A negative divided by a positive is negative overall. So to the right of x equals negative 3, I'm going to negative infinity. So I'm going to just draw this down arrow to signify that. And then to the left of my 0, I plug in 1.9 for x. 1.9 minus 2 is negative overall, and 1.9 plus 3 is positive. So overall, that is negative. Now out of 0, you don't have yourself shooting to negative or positive infinity. You have yourself going above or below the x-axis. But since I was negative, I'm going to be below the x-axis. And then do the same thing to the right of the 0 to determine the behavior. And this is always the case. You always need to determine the behavior to the left and right of the zeros and vertical asymptotes if you're trying to, by hand, sketch a rational function. So if I do h of 2.1, up top 2.1 minus 2 will be positive, and then 2.1 plus 3 will also be positive. And a positive divided by a positive is positive. So to the right of that 0, which is at x equals 2, so I'm going to be positive, which means I'm going to be above the x-axis. So that gives us the behavior to the left and right of the vertical asymptote and of the zeros. So then the next step I want to move on to is our step 4, which has us determining what are the y-intercepts. So if we hit the determine y-intercept, because we already did the x-intercept when we got the zeros, if we want a y-intercept, we have to let our x be 0. And you can go to the factored form, but you're basically evaluating your function at 0. So the factored form is x minus 2 over x plus 3, but instead of putting in x, we're going to go ahead and put in this 0. So if x is going to be 0, we're going to go ahead and put in 0 for x. And so we go ahead and we simplify, and that gives us negative 2/3. So the point for the y-intercept is 0, comma, negative 2/3. So let's say this is negative 1. That puts us about here, let's say. And then moving on from there, we have to determine whether we're going to have either a horizontal asymptote or oblique asymptote. From our function, once it's in canceled factored form, so we're looking at h of x is x minus 2 over x plus 3. The power in the numerator is not greater than the power in the denominator, so I know I will have a horizontal asymptote. Only when that power is greater do I have oblique. So I know I'm going to be dealing with a horizontal asymptote, and so I'm going to go ahead and work up here to deal with that horizontal asymptote. So I'm going to put HA for horizontal asymptote, and I'm going to look at our function h of x is x minus 2 over x plus 3. There's a couple ways to do this. The quickest way is if you know that the power of your leading term in the numerator is the same as the power of the leading term in the denominator, which is the case here. They both have a power of 1. Then your horizontal asymptote is going to be of the form y equals the coefficient of your leading term in the numerator, which is 1. This is a 1 here. And then over the coefficient of your leading term in the denominator. So 1 over 1, which is 1. So I know for a fact that I have a horizontal asymptote at y equals 1. So that's one way to do it. The other way is using a limiting approach, kind of the limit approach. So I'm going to rewrite my function again. H of x equals x minus 2 over x plus 3. And then what I'm going to do a little different here is I'm going to go ahead and divide by my highest power of x that I have, which is x to the first. And that's from either the numerator or the denominator, who's the highest power of x. And so the highest power of x is x to the first that any of my terms has. So I'm going to go ahead and divide by x. And x divided by x is 1. And then if I have an x of any power left in the denominator after canceling, then that term is going to go to 0. So minus 2 over x, nothing cancels out. I have that x in the denominator, so I know that term goes to 0. And the reason being is as x goes to infinity, 2 divided by something really large approaches 0. That's why it's a limit approach. X divided by x would be 1, and then 3 divided by x, I have that x left in the denominator, so that I know that's going to go to 0 as x gets really large. So again, this is 1 divided by 1, which is 1. And that takes a little longer, but that's the approach you can always use. So it's kind of nice. You don't have to memorize anything. You just have to do the math. But some people prefer to memorize. So I don't care how you do it, whichever way works for you. So then from there, I need to go ahead and connect the dots of the information I have found. So I have my vertical asymptotes, I have my horizontal asymptote, I don't have an oblique asymptote, I've got my y-intercept and my x-intercepts, aka my zeros. And so I just need to kind of connect up my graph. So if you start on the left side here, you see you have this vertical asymptote. You need to basically follow that down and follow your asymptotes to lead your graph. And so you can see I get this piece of the graph. And then notice I had this vertical asymptote here that was shooting down to negative infinity. Connect that up to your y-intercept, and then connect that up to the zeros, and then follow the horizontal asymptote. And that probably should be like a smoother curve, but you get the idea. But that's a rough sketch of your rational function using this 5-step approach.